This is the student's t-test question in the stats workbook, and we've got a comparing two sets of data, new expensive kit and old bit of kit for measuring haemoglobin. If we were to draw a graph of this, let's just do a little sketch. First thing we need to do is calculate the means. So what you do, let's just do one just to remind you about calculating your mean. Calculating the mean of these, 17.6 plus 13.9 plus 15.4 plus 16.5 plus 13.5 plus 16.5, 934, oh sorry, 93.4 divided by how many bits of data? We got 6. So our data mean is 15.6. So our mean there is 15.6. Okay. So mean there 15.6. I've done that with the old bit of kit as well, and the mean was 14.4. If we were putting that onto a bar chart, we'd have bottom axis is kit, and this is new, expensive, and old bit of kit. And we draw a bar chart. Up the side, we've got haemoglobin reading. Always just copy what you've got on the data table. And the new expensive kit will be 15.6, so we've got 0, 5, 10, 15, 15.6, so up there somewhere, so we draw a bar there. And the old kit 14.4, which would probably be there somewhere. So those two means actually look pretty similar. So already we're thinking there's probably not that much significant difference between them. We need to do a test on these. First of all, previously with data like this, we've calculated standard deviations. And you could do this here. You don't need to be able to calculate standard deviation, you just need to work with them. So we can actually do that for you. N, how many bits of data have we got? Well, we've got 6. And those standard deviation, we've calculated those for you, 1.6 and 1.7. And if you previously we've looked at the standard deviations, and if we put them on here, 1.6 would probably be about that much, and 1.7 would be about that much. And then if we did 2 times standard deviation, that's the standard deviation. If we did 2 times, well, even 1 time, they overlap, and so there's probably not much difference between these two means. Certainly if we did 2 times standard deviation, there'd definitely be a large overlap, and that reduces our opinion of how significantly different these means are. So back to what are we going to do? Well, here's our trusty chart of choosing the appropriate stats test. We're looking for associations between the expensive kit and the old kit. No. Difference between two means. Yes, we've got a mean for that one, and we've got a mean for the old bit of kit as well. So we're looking for any difference between these. Yes. And frequencies and categories. No, there's no categories there. So we're going to use our t-test. Null hypothesis. Well, we're looking for any difference between the means. So null hypothesis is there's no difference between the means. So no significant difference. There is no significant difference between the means for whatever and whatever. Means for haemoglobin readings for the new expensive kit and old bit of kit. So there's no difference between these means. And to calculate t, there's this kind of horrible looking equation. You don't need to be able to calculate t, you just need to be able to work with t, but we'll just have a quick zip through what you would do. So in here, on the top we've got the means, so the first mean and the second mean, so we can actually put those in. We can put in 15.6 and 14.4. 14.4. And underneath we've got S's, which are the standard deviations, and N, which is our N here, which is our number of samples. So it's the standard deviation squared divided by the number of samples for the first set of data, and then the same again, standard deviation squared divided by the number of samples for the second one. Then you're going to add those together and then square root them, which is a horrible bit of maths to do if you don't enjoy doing that. You can break it down into sort of steps here. So you've got S squared, standard deviation squared. We do that for you, 2.56 and 2.89, and then this bit, the squared divided by the number of samples, we can do that for you as well, 0.43, 0.48. So when we do that, we can put these in here. This would be 0.43, 0.48. We can work out the top. So 15.6 minus 14.4. You could shove that into your calculator. 15.6 take away 14.4 is 1.2. We could add these two together at the bottom. 0.43 plus 0.48 is 0.91. You could square that, and then that would give you 1.2 divided by 0.95. So 1.2 divided by 0.95, and that gives you 1.26 as your t value. So you don't need to do that, we don't think. You're just going to have to work with values of t. So you can work out the mean, you know what standard deviations are, you can do a null hypothesis, and if we give you t, then you can work out whether these are significant or not. You may need to choose degrees of freedom, and here's a degrees of freedom chart, and we've got degrees of freedom going up there. The rules are for the t-test, it's the total number of samples minus 2. So we've got so degrees of freedom is total samples minus 2. So our total samples is 6 of those and 6 of those. So 6 plus 6 minus 2 is 10. So how many degrees of freedom? This is our 6 plus 6 minus 2 equals 10. Use a table to find out the critical value for t. So for 10, that's going to be here. So we're looking at 2.23. And this is one where if t is bigger than the critical value, we can reject our null hypothesis, or indeed the other way around. And so our calculated value of t is actually, where is it? 1.26. It's less than 2.23. So it's less. So t-value of 1.26 is less than our critical value of 2.23, because that would be 1.26 and that is 2.23. And then there is more than 5%. We haven't given you a choice there, but it is more. Good job we put the right one in. More than 5% probability that the difference in the means are due to chance. We accept our null hypothesis. So that means that these are not significantly different.